this example, we're going to illustrate how to find the determinant of a matrix by using our row operations. For reference, we will be using the theorem 3 on page 171 of your textbook. And what does this theorem tell us? This theorem tells us is that the first thing is if B is obtained from A by doing a row replacement, then we can conclude that in that case, the determinant of A is equal to the determinant of B. This is if we use row replacement to get B. If B is obtained from A by doing a scaling of row of A, then in this case, we have that the determinant of B is equal to K times the determinant of A. And the last one is that if B is obtained from A by interchanging two rows of A, then the determinant of B is equal to negative the determinant of A. Now, from this theorem, since the only one that doesn't change to the determinant, which is the first one using row replacements, a lot of times when we do our row operations, we want to only use the row replacements as our method to create our new matrix. Another theorem we're going to be using is the triangular theorem. The theorem for the determinant of a triangular matrix, which says that the determinant of a triangular matrix is the product of the entries on the main diagonal. So ultimately the goal is to use our row operations to start with the matrix, use the row operations, get it into a triangular matrix, and then find the determinant. So let's look at an example. Let our matrix let our matrix A be the matrix 1, 3, 0, 2, negative 2, negative 5, 7, 4, 3, 5, 2, 1, and 1, negative 1, 2, negative 3. Now we can go ahead and try to put this matrix in row echelon form using our row operations. So because we have a pivot at the 1, we have a pivot here. Then we know that's our pivot, so we want to have zeros underneath that 1. So 1, 3, 0, 2, negative 2, negative 5, 7, 4, 3, 5, 2, 1, 1, negative 1, 2, negative 3. Only using row replacements. So our row operations are going to be 2 times row 1 plus row 2 to replace row 2. Negative 3 times row 1 plus row 3 to replace row 3. And negative 1 row 1 plus row 4 to replace row 4. Gives us the matrix 1, 3, 0, 2, 0, 1, 7, 8, 0, negative 4, 2, negative 5, 0, negative 4, 2, negative 5. Now, in this step, because we only use row operations to go from matrix A, our matrix A to this new matrix B, these two matrices will have the same determinant. Now our matrix B is not triangular yet, so we'll do another row replacement. We have a pivot here at that 1, so that means we can get zeros underneath that pivot. So our row operations this time are going to be 4 times row 2 plus row 3 to replace row 3, 4 times row 2 plus row 4 to replace row 4. This gives us the matrix 1, 3, 0, 2, 0, 1, 7, 8, 0, 0, 30, 27, 0, 0, 30, 27. All right. And again, we can continue to put this in row echelon form. We have our next pivot at 30, so we can make the 30 underneath that one 0. So then only using row replacements, this gives us the matrix 1, 3, 0, 2, 0, 1, 7, 8, 0, 0, 3, 30, 27, 30, 27, and then we have a row of 0, 0, 0, 0, 0. And just for your reference, that row was negative row 3 plus row 4 to replace row 4. Now, at every step, we only did the row operations, row replacements at every step. So since we only did row replacements from beginning to end, our first matrix will have the same determinant as our last matrix. Let's call the matrix at step 3C, and then our last matrix is matrix D. So matrix A and D have the same determinant. Now, since matrix D is triangular, we know that the determinant of D is the product of its entries on its main diagonal. So it's going to be 1 times 1 times 30 times 0, which gives us 0. Similarly, since matrix A and D have the same determinant, because we're only using row replacements, we can conclude that the determinant of A equals the determinant of D, which equals 0. So the determinant of our matrix A is 0. Another conclusion we can make to tie this in to chapter 2 is that since the determinant of A is 0, we know that A is not invertible. Okay.